The planet Venus is almost exactly the same size as Earth. It orbits within the same general region of the solar system. It has an atmosphere, weather patterns, and a solid surface. For most of the 20th century, scientists assumed it was a plausible candidate for some form of life. They were wrong about nearly everything they thought they knew about it. In the mid-20th century, the dominant scientific model described Venus as a warm, tropical world. Because its surface was hidden beneath a permanent layer of thick cloud cover, astronomers made logical inferences about what lay beneath. The clouds suggested humidity. The distance from the sun suggested temperatures that were warm, but not deadly. Theoretical models pointed toward a planet blanketed in jungle vegetation, or at the very least, covered in vast shallow oceans. This was not a fringe theory, it was the accepted scientific consensus. Soviet mission planners built their early probes around it. Instruments were calibrated to detect water vapor and biological signatures. The first generation of Venus probes carried equipment designed for a wet planet. The surface temperature of Venus is approximately 475 degrees Celsius. That is not a warm tropical environment. That is hot enough to melt lead. It is hot enough to melt zinc and tin. The pressure at the surface is 90 times greater than the pressure at sea level on Earth. To put that in physical terms, standing on the surface of Venus would be equivalent to being submerged 1 kilometer beneath the ocean while simultaneously being inside a furnace. The atmosphere is composed almost entirely of carbon dioxide, with clouds made of concentrated sulfuric acid. There is no water. There is no possibility of liquid water existing anywhere on the surface. The planet is, by every measurable standard, one of the most hostile environments in the solar system. Understanding how scientists discovered this reality, and what they actually saw when they finally got cameras down to the surface, is one of the most extraordinary stories in the history of planetary exploration. The first Soviet probe designed to reach Venus was Venera 4, launched in 1967. The engineering team had worked from the best available atmospheric models at the time. Those models estimated the surface pressure of Venus at approximately 20 times the atmospheric pressure of Earth. This was considered a challenging but manageable engineering problem. The probe was built to withstand that estimate, reinforced with aluminum alloys and designed to descend slowly under a parachute, transmitting data during the long drift to the ground. Venera 4 entered the Venusian atmosphere and deployed its parachute as planned. It began transmitting temperature and pressure readings as it descended. Then the transmission stopped. Ground controllers analyzed the data and realized the probe had not reached the surface. It had stopped transmitting at an altitude of approximately 27 kilometers above the ground. The probe had not burned up. It had been physically crushed by atmospheric pressure that far exceeded its structural limits. At 27 kilometers of altitude, the pressure was already beyond what the probe could handle. The surface was still more than 20 kilometers below. The data from Venera 4, combined with ground-based radar measurements, forced a complete revision of the atmospheric model. The surface pressure was not 20 atmospheres, it was closer to 90. This single fact rewrote the engineering requirements for every future mission to Venus. The team had a limited window before the next planetary alignment would allow a launch. There was not enough time to build an entirely new pressure vessel from scratch. For Venera 5 and Venera 6, the engineers tried a different approach. They reduced the size of the parachute, dramatically increasing the probe's descent speed. The reasoning was straightforward. If the probe fell faster through the upper atmosphere, it would spend less time in the region where pressure was building, and it might reach the surface before the hull gave way. Both probes failed in the same way. They imploded roughly 11 kilometers above the surface. The atmosphere crushed them before they had any chance of reaching the ground. These failures forced a fundamental rethink. The engineers stopped approaching the problem as an aerospace challenge and began approaching it as a deep-sea engineering problem. The vehicle they needed was not an aircraft, it was a submarine. Venera 7 was built around a forged titanium sphere capable of withstanding 180 atmospheres, double the expected surface load. To keep the weight manageable, nearly all scientific instruments were removed. The windows were eliminated. The solar panels were replaced by heavy internal batteries. The sphere was stripped down to its essential function, which was to survive. Venera 7 launched in August of 1970 and arrived at Venus in December of that year. The descent began, and almost immediately something went wrong. The parachute reefing cords melted in the heat of the upper atmosphere, causing the parachute to partially collapse during the final stage of descent. The probe did not float gently down to the surface, it fell. It struck the surface at approximately 17 meters per second. In mission control, the telemetry stream flatlined immediately after impact. Controllers marked the mission as a failure and began reviewing what little data had been captured during the descent. It was during a post-mission analysis of the raw radio recordings that an astronomer noticed something unusual. In the static and noise of the failed transmission, there was a faint signal. The probe had not been destroyed. It had toppled onto its side on impact, pointing its antenna away from Earth. It was still transmitting, but the signal was so weak and distorted, it had been dismissed as background noise. By carefully processing the noise in the recordings, the team recovered 23 minutes of temperature data from the surface of Venus. It was the first time in history that a human-made machine had transmitted information from the surface of another planet. The data confirmed the surface temperature at approximately 475 degrees Celsius. It proved that a machine built with sufficient structural integrity could survive the conditions. It also proved that any camera or instrument system sent to this world would need to be engineered with extreme care. The problem of temperature was in many ways more difficult to solve than the problem of pressure. A titanium sphere could resist the crushing force of 90 atmospheres, but heat is harder to contain. Silicon electronics, the foundation of computing and imaging technology, begin to fail rapidly above roughly 120 degrees Celsius. The surface of Venus sits nearly 4 times hotter than that. Standard insulation merely slows the transfer of heat. On a long enough timescale, the internal temperature of any insulated container will equalize with the environment around it. Active cooling systems, such as refrigeration units or radiators, could not work on Venus for a fundamental thermodynamic reason. A radiator dumps heat into the surrounding environment. That only works when the surrounding environment is cooler than the object being cooled. On Venus, the air outside the probe is hundreds of degrees hotter than the electronics inside. A radiator would pump heat into the lander rather than out of it. The Soviet engineers developed a 2-stage thermal management system. Before the lander separated from the orbiting spacecraft, the system circulated supercooled fluid through the pressure vessel, reducing the internal temperature to approximately -10 degrees Celsius. The lander began its descent as a chilled container. It had a thermal head start. As the descent progressed and heat began penetrating the titanium shell, a phase change material absorbed that energy. The interior of the lander was packed with lithium nitrate trihydrate, a chemical with a melting point of 30 degrees Celsius. When a substance melts, it absorbs a large quantity of energy in the process of changing state without increasing in temperature. This is the same principle that makes ice useful for keeping things cold. The ice absorbs heat while melting, maintaining a stable temperature until it is fully liquid. The lithium nitrate trihydrate performed the same function inside the probe. As the Venusian heat penetrated the shell, the chemical absorbed it, melting slowly and keeping the interior relatively stable. This system gave the engineers a working window of approximately 50 to 60 minutes before the phase change material was fully consumed and the internal temperature began climbing rapidly. 60 minutes on the surface of Venus. That was the operational window. Every instrument, every camera, every drill and sensor had to accomplish its objectives within that span of time before the lander became a sealed oven and the electronics began to fail. The imaging system presented its own category of challenges. A standard television camera from the 1970s used cathode ray tube technology. These tubes were bulky, fragile, and required large glass lenses to focus light. The pressure vessel of a Venus lander could not safely accommodate a large glass window. Glass under those conditions would be a structural weakness. A crack or seal failure would cause immediate and catastrophic implosion. Instead of a camera, the engineers built what is technically called a telephotometer. The device was entirely mechanical in its core operation. It was mounted inside the cooled pressure vessel and looked outward through a small cylindrical quartz window. Quartz could withstand the pressure without failure. A small mirror rotated behind the window. The mirror reflected light from a single point on the Venusian surface into a sensor inside the vessel. The sensor measured the brightness of that one point. Then the mirror shifted slightly and measured the next point. The probe transmitted this as a stream of numbers, essentially a long list of brightness values for each point in sequence. On Earth, computers received this numerical stream and reconstructed the image, line by line, assembling the data into a panoramic photograph. The process was slow. Depending on resolution and scanning speed, building a complete panoramic image could take 20 to 30 minutes. If the probe overheated before the scan completed, the image would simply cut off mid-frame. The engineers accepted this trade-off. A mechanical scanner was far more likely to survive the conditions than a complex electronic imaging system. It sacrificed speed for durability. On October 22, 1975, Venera 9 completed its descent and landed on the surface of Venus. It survived for approximately 50 minutes. When the lens cover was ejected by a pyrotechnic charge and the scanner began its first sweep, the engineers received their first surprise. The assumption had been total or near total darkness on the surface. The atmosphere was 90 times denser than Earth's. Models predicted that it would block virtually all incoming sunlight, leaving the surface in perpetual twilight or complete blackness. Venera 9 carried powerful halogen floodlights specifically to illuminate the ground for the camera, because no one expected natural light to be sufficient. The floodlights were unnecessary. The surface of Venus was not dark. The ambient light reaching the ground, scattered and diffused through 90 atmospheres of carbon dioxide, was comparable to a cloudy summer afternoon on Earth. The thick atmosphere did not block sunlight. It scattered it in every direction, creating a soft, even illumination with no harsh shadows and no direct sunbeams. The surface was genuinely visible in its own ambient light. The image that assembled on the screens in Mission Control overturned a second assumption. Scientists had expected the surface of Venus to look like a worn, eroded desert. The atmospheric pressure was so extreme, and the atmosphere so dense, that models predicted strong surface winds capable of scouring the rocks down to fine powder over geological time. The expectation was smooth, rounded stones, or drifts of dark volcanic sand. Venera 9 showed the opposite. The ground was covered with sharp, angular rocks. The edges were jagged and fractured. These were not ancient worn stones. These were geologically young surfaces, rocks that had recently broken apart and not yet had time to erode. The implication was significant. The surface of Venus was not a static ancient wasteland. It was geologically active. The landscape was being renewed on timescales that prevented significant erosion. Furthermore, the fact that the rocks were sharp proved that the surface wind speed was negligible. If strong winds had been present, the rocks would have been smoothed. They were not. The lower atmosphere, despite its crushing density, was essentially calm. 3 days after Venera 9 landed, Venera 10 touched down more than 2,000 kilometers away. It operated for 65 minutes. Its images showed a completely different terrain. Instead of a pile of angular fractured boulders, Venera 10 sat on a smoother surface covered in flat slabs of what appeared to be solidified lava. These were older formations, worn and flattened by geological processes. The two landing sites proved that Venus was not a uniform world. It had distinct geological regions with different ages and different histories, much like Earth. These two black and white images were the first direct photographs ever taken of the surface of another planet. But they left a fundamental visual question unanswered. What color was Venus? The answer arrived in March of 1982, when Venera 13 and Venera 14 landed 4 days apart in different regions of the planet. These missions were the apex of the Soviet Venus program. They were heavier and more sophisticated than their predecessors, and they carried upgraded telephotometers capable of capturing color. The color system worked by taking multiple sequential scans of the same scene, each scan through a different colored filter: red, green, and blue. The 3 datasets were transmitted to Earth separately and recombined by computer into a composite color image. The technique was standard for scientific color imaging of the period, borrowed from methods used in astronomical photography. Venera 13 landed on March 1, 1982, and achieved a record-breaking survival time of 127 minutes on the surface. The scanner began its sequence immediately. As the color composites assembled on Earth, scientists saw a result that none of the atmospheric models had predicted in its specifics. The surface of Venus was bathed in a deep, suffocating orange light. Everything in the image was some shade of orange or dark reddish-brown. The rocks were orange. The sky was orange. The horizon dissolved into an orange haze. It was not a malfunction of the imaging system. The color calibration target on the probe, a panel with strips of white, red, green, and blue paint that was within the camera's field of view in every scan, confirmed the reading. In the Venera 13 images, the white strip on the calibration target appeared orange. The blue strip appeared nearly black. The green strip was darkened and distorted. The atmosphere of Venus was acting as a massive optical filter. As sunlight passed through the thick layers of cloud and carbon dioxide, it absorbed the shorter wavelengths of light, the blues and greens, preferentially. By the time the light reached the surface, only the longer red and orange wavelengths remained in significant quantities. The Venusian atmosphere had filtered the spectrum of the sun down to its warmest colors. The implication for any hypothetical human observer standing on the surface would be striking. The entire visual world would appear in tones of amber and rust. The brain compensates for color shifts when there is a white reference, the way it adjusts perception in different artificial lighting conditions. On Venus, there is no white reference. Every surface reflects the same orange filtered light. A human visitor would perceive the entire landscape in sepia tones, unable to mentally correct for the atmospheric shift. Venera 13 also carried a microphone, a device called the Groza, designed primarily to detect seismic events and lightning discharges in the atmosphere. It also functioned as a general audio recorder. When activated, it captured the first sounds ever recorded on the surface of another planet. The recording captured two distinct categories of sound. The first was wind noise. Instruments confirmed a wind speed at the surface of approximately half a meter per second. On Earth, this would be imperceptible, barely enough to rustle a leaf. On Venus, the atmospheric density changes the physics entirely. The atmosphere is approximately 60 times denser than Earth's at the same wind speed. A half-meter per second wind on Venus exerts significant physical force, comparable to a much stronger wind on Earth. The microphone picked up a deep, constant aerodynamic drone as the thick air flowed around the lander structure. The second category of sound was mechanical. Venera 13 successfully deployed a pneumatic drill to collect a soil sample. The microphone captured the sharp sound of the pyrotechnic charge that fired the drill mechanism. It then recorded the grinding and percussive sound of the drill bit cutting into what analysis later confirmed was basaltic rock, similar in composition to volcanic rock found on Earth. The audio confirmed that dense atmospheric conditions made Venus an excellent acoustic conductor. Sounds that would be muffled in thin air were transmitted with unusual clarity through the thick carbon dioxide medium. The soil analysis from the drill sample was significant. Basalt is the most common volcanic rock on Earth and is produced by the cooling of magma. Its presence on Venus confirmed that the planet had experienced extensive volcanic activity. The surface was not a chemically exotic alien landscape. It was, in terms of rock composition, surprisingly similar to the volcanic regions of Earth. Venera 14 landed 4 days later on March 5, 1982, roughly 1,000 kilometers from the Venera 13 site. The terrain was different. It was flatter and smoother, resembling cracked pavement of basaltic material. The mission profile was identical. Photograph the surface, analyze the atmosphere, drill a soil sample, and physically test the ground with a mechanical arm. The mechanical arm was a spring-loaded device mounted on the base of the lander. It was programmed to swing down and strike the ground with a calibrated force. By measuring how far the arm penetrated the surface material, scientists could determine the compressibility and density of the Venusian soil. It was a simple, robust test designed to tell engineers whether the ground was hard rock or soft dust, information essential for designing future landers. The landing sequence ran through its automated steps. The footing stabilized. The pyrotechnic charges fired to eject the lens caps that had protected the camera optics during the descent. On Venera 14, the lens cap ejected cleanly. Then, rather than rolling to one side or bouncing away, it settled directly onto the patch of ground that the compressibility arm was programmed to strike. A few moments later, the arm deployed. It swung down with full mechanical force and struck the object directly beneath it. The telemetry transmitted to Earth indicated that the surface of Venus had essentially zero compressibility. According to the data, the Venusian ground was extraordinarily hard and rigid, with no measurable give whatsoever. The camera images made the situation clear. The probe had measured its own titanium lens cap. The arm had perfectly targeted the piece of protective hardware the mission had brought from Earth and then discarded on landing. The actual Venusian surface lay only centimeters away, untouched by the arm. The entire compressibility measurement for Venera 14 recorded the properties of a machined titanium component, not the planet it had traveled hundreds of millions of kilometers to study. It is arguably the most famous mechanical failure in the history of planetary exploration. Every technical challenge had been overcome. The probe had survived launch, a journey through interplanetary space, atmospheric entry, a high-temperature descent through 90 atmospheres, and a successful landing. Then a piece of its own safety equipment defeated the primary surface science objective by landing in exactly the wrong place, at exactly the wrong moment. The restored panoramic images from Venera 13 became the focus of a surprising and controversial scientific debate 30 years after they were taken. In 2012, a researcher named Leonid Ksanfomalidi published an analysis of the original Venera 13 image sequence that received significant attention. Ksanfomalidi was not a fringe figure. He had been a legitimate contributor to the Soviet space program and had a record of published scientific work. His analysis focused on the sequential nature of the Venera 13 imaging. The telephotometer had not taken a single snapshot. It had scanned the same scene repeatedly over the course of the lander's 127 minutes of operation. By comparing these sequential scans, Ksanfomalidi was looking for changes in the scene over time, changes that might reveal dynamic processes occurring on the surface. He identified several objects that appeared to change position or shape between scans. The most prominent he named the Scorpion. In the earliest scans of a particular patch of ground, the area appeared empty. In a scan taken approximately 7 minutes after landing, a structured object appeared. It was approximately 15 centimeters in length and seemed to have a central elongated body with a curved extension. In subsequent scans, it was no longer visible in the same location. Ksanfomalidi interpreted this as evidence that the object had emerged from the surface material, remained visible for a short period, and then moved out of the camera's field of view. He identified another anomalous feature he called the black flap, which also appeared to change shape and position across the scan sequence. His published conclusions suggested the possibility that these objects could represent some form of life adapted to the extreme Venusian conditions, operating on chemistry fundamentally different from carbon-based terrestrial biology. The scientific community's response was almost uniformly skeptical. Researchers at NASA and other institutions with expertise in spacecraft behavior under thermal stress offered a detailed mechanical explanation. The Venera landers were wrapped in layers of insulation, foam, and thermal protection material. As the internal temperature of the lander climbed over the course of its operational life, these materials began to degrade, melt, and physically detach from the lander structure. Pieces of insulation and plastic fell away from the probe during its time on the surface. The movement was not biological locomotion, it was the thermal disintegration of the spacecraft itself. The changing shadows in the image sequence could be explained by the gradual movement of the sun's position in the sky over the 127-minute observation period, combined with the settling of the lander structure as the soil beneath its feet compressed slightly under the probe's weight. Subsequent reanalysis using improved digital restoration techniques has confirmed that the anomalous features are consistent with detached components of the lander, artifacts in the image data caused by the scanning process, or noise introduced during transmission. No features in the Venera 13 images have been confirmed as evidence of biological activity. The controversy, however, drew attention back to something the images genuinely showed, which was that the surface of Venus during the Venera 13 landing was not a static scene. The lander was interacting dynamically with its environment. The extreme temperatures were visibly affecting the probe's external materials in real time. The environment was actively destroying the machine that had come to study it, and the slow-scanning camera was inadvertently capturing that process of destruction frame by frame. What the images recorded in their final scans, the shifting surface debris and the warping materials, were the last observations of a machine in the final stages of thermal failure. The impossible-seeming movements were the dying behavior of engineering systems under conditions they were never designed to endure indefinitely. The probe had survived longer than any of its predecessors. In the end, Venus claimed it anyway. After Venera 14, the Soviet program shifted direction. The engineering teams recognized a fundamental limitation of the lander approach. Surface stations provided extraordinary close-up data from single points. But understanding the geology of an entire planet required mapping its full surface. To do that, they needed orbital platforms carrying radar systems capable of penetrating the permanent cloud cover. Venera 15 and Venera 16 launched in 1983. They carried no landers. Instead, each probe was equipped with a synthetic aperture radar system, a type of imaging radar that uses the motion of the spacecraft to synthesize a much larger effective antenna, achieving resolution far beyond what a physical antenna of that size could produce. These two probes mapped the northern hemisphere of Venus in unprecedented detail. The radar maps revealed a world of extraordinary geological complexity. There were shield volcanoes, massive low-profile volcanic structures similar in form to those found in Hawaii on Earth. There were lava channels stretching for thousands of kilometers across the plains, formed by rivers of extremely fluid lava flowing across the surface billions of years ago. There were tectonic fracture zones, regions where the crust of Venus had been pulled apart or compressed by internal forces. And there were unique features called tesserae, complex interlocking regions of highly deformed terrain that have no clear analog on Earth, likely produced by unusual tectonic processes that operated very differently from the plate tectonics familiar on our own planet. The data from Venera 15 and Venera 16 was scientifically invaluable, but it was abstract in a way that the lander images were not. A radar topographic map tells scientists about elevation, surface roughness, and the reflectivity of materials. It does not show color, texture, or the appearance of the landscape as it actually looks. The radar data expanded the scientific understanding of Venus enormously, but it did not add to the visual record of what Venus actually looks like from the ground. The final Soviet missions to Venus, Vega 1 and Vega 2, launched in 1985 on a dual-purpose trajectory. Their primary scientific objective was to intercept Halley's Comet, which was making its periodic passage through the inner solar system at that time. On their way to the comet, both spacecraft made flyby maneuvers at Venus and released landing packages. These landers focused on atmospheric chemistry and soil composition. They also deployed instrumented balloons that floated through the middle cloud layers of the Venusian atmosphere, measuring wind speeds, temperature gradients, and pressure at altitude. The balloon data revealed that the upper atmosphere of Venus has remarkably dynamic weather, with fast-moving horizontal winds and complex circulation patterns. The Vega landers did not carry cameras. The mission designers made a deliberate decision to use the weight allocation that imaging systems would have required for additional chemical analysis instruments. The balance of scientific priorities had shifted. The visual question of what Venus looked like had been answered by the Venera series. The Vega missions were focused on composition and chemistry. With the political and economic upheaval of the late 1980s and the eventual dissolution of the Soviet Union, the Venera and Vega programs came to a permanent end. The archives of mission data, stored on magnetic tape, began to degrade physically over time. The original tape recordings contained the raw telemetry signals, the streams of numbers that had been transmitted across the distance between Venus and Earth. Those signals were the source material for every image from the program. The images that had appeared in scientific publications and newspapers during the 1970s and 80s were often processed under time pressure using the computational tools available at the time. The results were grainy, low contrast, and geometrically distorted. The mechanical scanning process introduced specific types of distortion that required correction, And the algorithms for performing that correction were limited by the processing power of 1970s and 80s mainframe computers. In the 2000s, a generation of researchers began working to restore the Venera image archive. They went back to the raw telemetry data wherever the original tapes could still be read. Modern processing algorithms could handle the noise in the signal far more effectively than the original equipment. New correction techniques could compensate for the geometric distortions introduced by the panoramic mirror system. Missing data points caused by transmission errors could be reconstructed using statistical interpolation based on surrounding values. The results of this restoration work were striking. Details that had been lost in the original processing became visible for the first time. The texture of the Venusian soil became clearer. The layering structure of the rocks in the foreground resolved into distinct strata. The horizon line in the panoramic images turned out to be further away than the original versions had suggested, meaning the visual range on the surface was greater than previously understood. The restored images reveal the landscape of angular basaltic rock under an orange-filtered sky, a scene that was simultaneously alien and geologically familiar. These restored images remain the only direct optical photographs taken from the surface of Venus. Every other image of Venus that appears in any scientific paper, textbook, or news article is either a radar-derived elevation map, a computer-generated artistic rendering based on radar data, or a photograph of the cloud tops taken from orbit. The gap in the visual record is remarkable when placed alongside what humanity has achieved elsewhere in the solar system. Mars has been photographed by landers and rovers almost continuously since 1976. The Curiosity and Perseverance rovers stream high-definition imagery from the Martian surface on a regular basis. The surface of Mars is one of the most extensively photographed landscapes outside of Earth. In 2015, the New Horizons spacecraft flew past Pluto and returned detailed color photographs of a world that had been little more than a blurry point of light for 85 years. Venus, which is the closest planet to Earth, which shares nearly the same diameter and mass as our world, which is close enough that spacecraft can reach it in a few months, has not had a single working camera on its surface since Venera 14 in March of 1982. That is more than 4 decades without a new ground-level photograph. The reason is not a lack of scientific interest. It is a matter of engineering difficulty. The challenges that the Soviet engineers solved in the 1970s and 80s have not become easier. Building a machine that can survive 475 degrees Celsius and 90 atmospheres of pressure for even 1 hour remains an extraordinary engineering problem. The materials science has improved, but the fundamental thermal management challenge is the same. Modern electronics are in some ways more sensitive to heat than the simpler systems of the 1970s. Building a lander that keeps those electronics functional in Venusian conditions is an active research problem without a simple solution. Several space agencies and private organizations have proposed missions to return to the Venusian surface with cameras and modern instruments. NASA's Da Vinci mission, which was selected as a priority mission in its planetary science survey, is designed to descend through the Venusian atmosphere on a probe, making measurements of the atmospheric chemistry on the way down, and potentially imaging the surface during the final stages of descent. This would not be a long-duration surface station, but it would provide new close-up visual data of the surface during the descent phase. NASA also selected the Veritas mission, which would place an orbiting spacecraft at Venus with advanced radar imaging capabilities significantly exceeding those of the Magellan spacecraft that mapped Venus from orbit in the early 1990s. The Veritas radar would resolve surface features at finer scales and provide new 3-dimensional topographic data. However, the schedule and funding for both of these missions has been subject to revision and uncertainty. Neither has yet launched. The European Space Agency's Envision mission is also planned as an orbital mission to study the geological history of Venus using radar and spectroscopy. Like Veritas, it would observe the planet from orbit rather than the surface. The question of what is happening on the surface of Venus today, in terms of active volcanism, atmospheric chemistry, and the detailed structure of the terrain, remains partially open. In 2010, instruments aboard the European Space Agency's Venus Express orbiter detected infrared signatures in certain regions of the Venusian surface that were interpreted as evidence of relatively recent or possibly ongoing volcanic. Eruptions. The signatures suggested that some volcanic features had surface temperatures slightly higher than their surrounding terrain, consistent with recent lava flows that had not yet cooled to the ambient surface temperature. These observations were made indirectly from orbit and required complex modeling to interpret, but they suggested that Venus may not be geologically dormant. In 2020, a team of researchers announced that they had detected phosphine gas in the upper atmosphere of Venus using radio telescope observations. Phosphine is a molecule consisting of one phosphorus atom and 3 hydrogen atoms. On Earth, it is produced primarily by anaerobic microorganisms, organisms that live without oxygen, or by industrial processes. Its presence in the upper Venusian atmosphere, at altitudes where temperatures and pressures are comparable to those in the upper atmosphere of Earth, prompted significant discussion about whether biological processes in the cloud layers might explain the signal. The claim was immediately contested. Other research teams reanalyzed the original telescope data and raised questions about the signal processing methodology. Some analyses concluded that the phosphine signal was significantly weaker than originally reported, or potentially absent entirely. The debate over the phosphine claim has not been fully resolved, but the consensus has moved toward skepticism about the original signal strength. No confirmed biological explanation has been accepted. The episode did, however, highlight the fact that the atmospheric chemistry of Venus is not as well understood as many assumed, and that the cloud layers of Venus deserve more detailed investigation. What is known with certainty is that the upper atmosphere of Venus, at altitudes between approximately 48 and 60 kilometers, hosts a region where temperatures range from 0 to 90 degrees Celsius, and pressures are comparable to Earth's surface. This is the most Earth-like environment in the solar system outside of Earth itself. Whether anything lives in those clouds, even in the most minimal microbial sense, is a question that cannot be answered from Earth with the instruments currently available. The question of how Venus became what it is today is also unresolved. Venus and Earth formed from similar material in similar regions of the early solar system. They are nearly identical in size and mass. Early models of planetary formation suggest they should have had similar inventories of water. Yet Venus today has almost no water at all, while Earth is covered in it. At some point in Venus's history, the planet lost its water. The process likely involved a combination of factors, including the planet's proximity to the Sun, which provided enough ultraviolet radiation to split water molecules in the upper atmosphere, and the lack of a strong magnetic field, which allowed the solar wind to gradually strip away the lighter hydrogen atoms that result from that splitting. Whether Venus had a more temperate past, with liquid water oceans on its surface, is an open scientific question. Some models suggest that early Venus, before the Sun increased its luminosity as it aged, could have maintained stable temperatures compatible with liquid water for several billion years. If that is true, Venus was once more similar to Earth than it is today, and the runaway greenhouse effect that turned it into its current state was a more recent development in geological terms. Understanding this transition matters for more than just the history of Venus. Earth's atmosphere contains increasing concentrations of carbon dioxide due to human industrial activity. The long-term consequences of that increase are an active area of climate research. Venus represents a natural extreme case of what happens when a planet's greenhouse effect runs unchecked, not a direct analog for Earth's situation, which involves different atmospheric compositions and different timescales, but a reference point for understanding the physics of atmospheric warming in planetary systems. The conditions on Venus are not the result of a slight perturbation of Earth-like conditions. They represent a stable planetary state that formed over geological time. Getting there from here would require processes operating over millions of years. But understanding how Venus reached this state informs the models scientists use to project the behavior of other planetary atmospheres, including our own. The Magellan spacecraft, launched by NASA in 1989 and arriving at Venus in 1990, spent 4 years mapping the entire surface of the planet using synthetic aperture radar. The resulting global topographic map remains the most complete picture of the Venusian surface available. It revealed a planet with a complex geological history. 2 major continental scale highland regions called Ishtar Terra and Aphrodite Terra, thousands of volcanoes of varying sizes, extensive lava plains covering most of the planet's lower elevations, and the mysterious tessera terrain that defies simple geological explanation. The lack of a planet-wide system of plate tectonics like Earth's remains one of the most puzzling aspects of Venusian geology. On Earth, the crust is divided into a set of mobile plates that slowly move relative to each other, driven by convection in the mantle beneath. This process continuously recycles old crust into the mantle and creates new crust at spreading zones. It is also responsible for the formation of mountain ranges, ocean trenches, and the distribution of volcanic activity. Venus shows no clear evidence of this kind of global tectonic system. Instead, its heat appears to escape through localized volcanic eruptions and occasional episodes of widespread resurfacing, where large portions of the crust are overturned by intense volcanic activity over relatively short geological periods. One prominent hypothesis, sometimes called catastrophic resurfacing, suggests that Venus goes through periodic episodes where internal heat builds up to the point where the entire crust becomes unstable and is overturned in a relatively rapid geological event, flooding most of the planet's surface with fresh lava before a new crust solidifies. If this hypothesis is correct, the relatively uniform age of the Venusian surface, estimated at around 500 million years based on the density of impact craters, reflects the most recent such resurfacing event. Prior to that event, the geological record would have been completely erased. This would make Venus fundamentally different from Earth in the way it manages its internal heat. Rather than the continuous process of plate recycling that operates on Earth, Venus would accumulate heat over hundreds of millions of years and then release it catastrophically in geological terms, resetting the surface and beginning the cycle again. Whether Venus is currently in a quiescent phase between these events or approaching another resurfacing episode is unknown. The atmosphere also contains mysteries that remain unresolved. The clouds of Venus are composed primarily of sulfuric acid droplets formed by chemical reactions involving water vapor and sulfur dioxide in the upper atmosphere. These clouds are extremely bright in visible light, reflecting approximately 70% of the sunlight that reaches Venus back into space. This high reflectivity, technically called albedo, is partly why Venus appears so bright in the night sky from Earth. Within these clouds, there are regions that absorb ultraviolet light in patterns that have not been fully explained by known atmospheric chemistry. The ultraviolet absorber in the Venusian clouds was first detected in the 1920 OS. Nearly a century later, its composition has still not been definitively identified. It appears at specific altitudes in the cloud layers and creates the banded and streaked patterns visible in ultraviolet photographs of Venus taken from orbit. Various chemical candidates have been proposed, including iron chloride compounds and certain sulfur compounds, and even microbial pigments in the more speculative literature. No candidate has been confirmed. The atmosphere of Venus also rotates dramatically faster than the solid planet beneath it. Venus rotates on its axis very slowly, taking approximately 243 Earth days to complete one rotation, which is actually longer than its orbital period around the Sun of 225 Earth days. This means a day on Venus, in the sense of one rotation relative to the stars, is longer than a Venusian year. The atmosphere, however, circulates around the planet in approximately 4 Earth days at the altitude of the cloud tops. This phenomenon, called superrotation, means the upper atmosphere moves roughly 60 times faster than the surface below. What drives and maintains this superrotation is an active research question. The mechanisms that would allow an atmosphere to sustain such rapid circulation relative to its planetary body are not fully understood and represent a significant gap in atmospheric science. The surface winds, by contrast, are nearly calm, as the Venera images confirmed. This combination, a violently fast upper atmosphere and a near-still lower atmosphere, is counterintuitive but is a consistent feature of Venusian atmospheric dynamics that any complete model of the planet must explain. Venus also has lightning. The Venera probes detected electromagnetic signals consistent with lightning discharges on multiple missions. The Groza instrument that captured the first Venusian sounds was also designed to detect these discharges. More recent orbital observations have provided additional evidence for lightning activity, though the exact mechanisms and frequency remain uncertain. On Earth, lightning in the lower atmosphere is produced primarily by charge separation in thunderstorm clouds. On Venus, the dense carbon dioxide atmosphere and sulfuric acid clouds operate under very different thermodynamic conditions, and the specific processes that might produce lightning there are not fully characterized. The possibility of missions that could operate on the Venusian surface for extended periods, rather than the 1 or 2 hours achievable with passive thermal management, depends on solving the temperature problem in a fundamentally new way. One approach involves developing high-temperature electronics using semiconductor materials that remain functional at temperatures above 400 degrees Celsius. Silicon carbide is one candidate material that has shown promise for operating at higher temperatures than standard silicon. Small electronic components made from silicon carbide have been tested and have demonstrated function at temperatures approaching those of the Venusian surface in laboratory conditions. Scaling this technology to the complexity required for a scientific instrument package remains a significant engineering challenge. Another approach involves placing the sensitive electronics inside a small, heavily insulated container within the main lander structure, with only the most basic thermally robust components exposed to the environment. This is essentially a more sophisticated version of what the Soviet engineers did, but with modern materials and much better thermal modeling. A third approach, studied by engineers at NASA's Glenn Research Center, among others, involves building a lander without conventional microelectronics at all, using mechanical logic systems analogous to the mechanical computers of the 19th century, but implemented in modern materials capable of surviving Venusian conditions. Such a machine would process information mechanically rather than electronically, making it inherently immune to the temperature problem at the cost of greatly reduced processing power and capability compared to modern electronics. None of these approaches has yet produced a mission-ready lander design. The engineering challenges of Venus remain substantial, but the scientific motivation for solving them has not diminished. Venus is the closest planet to Earth in size, mass, and likely in early history. Understanding it in detail, with instruments on its surface rather than radar systems in its orbit, would address some of the most fundamental questions in planetary science about how terrestrial planets evolve, how atmospheres develop, and what conditions are required for a rocky planet to remain habitable over geological time. The images from the Venera program, now restored and studied by a new generation of researchers, remain the starting point for any discussion of what Venus actually looks like. 40 years of progress in radar mapping, orbital spectroscopy, and atmospheric modeling have added enormously to the scientific picture of Venus. But the ground-level view has not changed. It is still the orange-lit rocky terrain of the Venera panoramas, the angular basaltic rocks under the diffuse amber sky, the cracked lava plains stretching to a horizon that turned out to be further away than first thought. The next camera to work on the surface of Venus will be the first new ground-level image of the planet in over 4 decades. It will show scientists whether the specific sites photographed by the Venera landers are representative of the broader terrain, or whether those sites were unusual in some way. It will reveal what the surface looks like at new latitudes and new geological contexts. It will, for the first time, allow comparison between the historical images and a contemporary observation, potentially detecting any changes that have occurred over the intervening period. Whether that next image comes in 10 years or 30 depends on engineering solutions that do not yet fully exist, and on the political and budgetary commitments of space agencies to prioritize Venus over the many other destinations, competing for resources and attention. What is certain is that the scientific questions Venus poses are real, important, and not answerable from the current archive of data alone. The planet closest to Earth remains, in the most literal visual sense, one of the least seen places in the solar system. The story of how humanity has tried to see Venus is also a story about the limits of what remote sensing can tell us, and what only direct observation can reveal. Radar can measure elevation. It can distinguish rough terrain from smooth. It can identify certain mineral compositions from the way surfaces reflect microwave energy. What radar cannot do is tell scientists the precise color of a rock, the texture visible to the eye, the way light plays across a surface under the actual conditions of the environment. Those things require a camera in the right place. This limitation applies across planetary science, not just to Venus. When scientists study Mars from orbit, they get broad coverage but lose detail at the scale of individual rocks. When a rover moves across the surface, it can examine things in detail, but covers only a tiny fraction of the planet. The trade-off between coverage and resolution is a constant in planetary exploration, and different missions are designed to address different parts of that trade-off. For Venus, the trade-off has been entirely in favor of coverage, because getting any instrument to the surface at all is so difficult. The Venera missions were surface missions by necessity as much as by choice. The engineers were trying to prove the concept, to demonstrate that a machine could survive and transmit data from the most hostile environment in the solar system that spacecraft could reach. They succeeded, imperfectly and partially, and they did it within severe technical constraints that no modern mission has yet chosen to confront directly. The record they established, 9 successful landings that returned data, 6 of those with imaging systems, across more than a decade of missions from 1970 to 1982, reflects an extraordinary sustained commitment to a single planetary destination under conditions of fierce technical adversity. Each mission built directly on the lessons of the previous one. Each failure contributed to the redesign that made the next mission slightly more capable. It was incremental engineering at its finest, driven by scientific curiosity and national competition in roughly equal measure. The competitive context of the Soviet Venus program shaped what it accomplished. The space race of the 1960s and 70s provided political motivation and financial resources for missions that might not have been funded on purely scientific grounds. Whether this was a healthy dynamic for science is a separate question. The result was that Venus received an intensity of attention from Soviet planetary science that it has not received from any space program since. NASA's Mariner and Pioneer Venus missions made significant contributions to understanding the Venusian atmosphere from above and from probe descent, but they did not place imaging cameras on the surface. The full sequence of surface imaging was entirely a Soviet achievement. The images in the Venera archive exist because Soviet engineers spent 15 years building progressively more capable machines designed to operate in conditions that were understood to be destroying the machine as soon as it arrived. The physical experience of the Venera landers on the surface, as inferred from their telemetry, must have been extraordinary in a purely mechanical sense. The probes arrived pre-chilled to below 0 degrees Celsius. They began absorbing heat immediately upon contact with the atmosphere. The internal temperature climbed steadily throughout the operational window. The phase change material inside absorbed energy and gradually melted. External surfaces of the lander began to degrade as temperatures exceeded the tolerances of protective coatings. By the time transmission ended, the probes were in an advanced state of thermal failure, their electronics barely functional, their structural components warping under the combination of heat and pressure. The last signals transmitted were the final output of systems operating at the edge of their physical limits. The images that arrived, line by line, over the communication link to Earth were being assembled by failing hardware on the surface of a planet that was actively destroying the machine producing them. That the images arrived at all, and that enough of them arrived to construct coherent panoramas, is a consequence of the mechanical simplicity and durability of the telephotometer design. A more complex electronic system would likely have failed sooner. The methodology of the image reconstruction also deserves attention for what it reveals about the nature of the data. The images are not photographs in the conventional sense of a camera capturing reflected light at a single instant. They are numerical reconstructions of a scene built from a long series of point measurements taken over many minutes. This means each image contains information from slightly different moments in time. If something in the scene moved during the scan, the resulting image would show a smeared or duplicated artifact at the location of the movement. This temporal aspect of the scanning process is directly relevant to the Xanthomelidae anomaly controversy. When he identified objects that appeared to change between consecutive scans, he was comparing images that were each themselves built from extended time sequences. Distinguishing genuine movement from artifacts introduced by the scanning process, equipment degradation, or changing illumination conditions is genuinely difficult without additional data. The subsequent analyses that attributed the anomalies to thermal degradation of the lander itself are methodologically reasonable given the known behavior of the probe, But the difficulty of the analysis reflects how challenging it is to extract reliable science from data that was assembled under such extreme and unusual conditions. Modern analysis techniques that have been applied to the restored Venera images include photogrammetric methods that attempt to derive three-dimensional information from the panoramic imagery. By analyzing the apparent shape and shadow of rocks at different positions in the panoramas, researchers have been able to make estimates of rock dimensions and surface topography in the immediate vicinity of each landing site. This adds a layer of scientific value to the images beyond simple visual interpretation. The rocks visible in the Venera panoramas are not just interesting to look at. They can be analyzed to extract information about their size distribution, their orientation, and the processes that formed them. The size and shape distribution of rocks in a geological setting carries information about the processes that produced them. Sharp, angular rocks suggest recent fracturing with minimal subsequent erosion. Rounded, smooth rocks suggest extended transport by water, wind, or ice. The angular rocks visible in the Venera 9 panorama are consistent with what would be expected from relatively recent tectonic fracturing in an environment with minimal erosion, which aligns with other evidence for geologically young surfaces at that landing site. The basaltic composition confirmed by the drill samples at multiple landing sites places Venus in the same broad geological category as the ocean floors of Earth and the surface of Mars. Basalt is produced when iron and magnesium-rich mantle material melts and erupts onto the surface, then cools relatively quickly. Its presence at the Venera landing sites confirms that the geological processes operating on Venus are recognizable analogs of volcanic processes operating elsewhere in the solar system, even if the specific history and dynamics are different. One of the persistent scientific questions about Venus is why it does not have a magnetic field comparable to Earth's. Earth's magnetic field is generated by the motion of conducting fluid in its outer core, a self-sustaining electromagnetic dynamo driven by a combination of heat flow from the inner core and the planet's rotation. Venus rotates so slowly that the rotation may not provide sufficient energy to maintain a similar dynamo. The result is that Venus has only a very weak induced magnetic field created by the interaction of the solar wind with its ionosphere, not a strong intrinsic field generated internally. The absence of a strong magnetic field has consequences for the long-term evolution of the Venusian atmosphere. Earth's magnetic field deflects the solar wind, protecting the upper atmosphere from direct bombardment by energetic particles. On Venus, the solar wind interacts more directly with the upper atmosphere, contributing to the gradual loss of atmospheric components over time. This stripping process is thought to be one of the reasons Venus has so little water today compared to its likely initial inventory. The hydrogen atoms liberated when solar ultraviolet radiation splits water molecules in the upper atmosphere are light enough to escape into space. Without a strong magnetic field, this process operates more efficiently. Whether a future magnetic field could be restored to Venus, or whether the slow rotation makes this permanently impossible, is a question about the deep interior of the planet that current data cannot answer. Understanding the internal structure of Venus, its core composition, the state of its mantle, and the dynamics of heat flow from the interior would require seismological data from the surface. A network of seismometers capable of detecting and characterizing Venusian earthquakes, or Venusquakes, would be scientifically enormously valuable but represents one of the hardest instrumentation challenges conceivable given the surface conditions. The comparison between Venus and Earth is ultimately a comparison between two possible fates for a rocky planet of similar initial conditions orbiting a similar star at a similar distance. Earth maintains stable conditions capable of supporting liquid water and life for billions of years. Venus, for reasons that are still not fully understood, ended up in a state of permanent, extreme thermal runaway. The transition between these two states is one of the central scientific mysteries of planetary science, and Venus is the primary laboratory for studying it. Getting a camera back to the surface of Venus, a camera that works long enough to capture high-resolution color panoramas of multiple geological settings, would be scientifically important not because the existing images are inadequate for what they are, but because the existing images represent only 6 small windows onto a planet covering more than 460 million square kilometers of surface area. Each of those windows was open for less than 2 hours. What lies beyond those windows in the other geological provinces of Venus, in its highland regions and its tessera terrain and its volcanic plains, remains visually unknown. The Venera images are the beginning of a visual record, not a complete one. They prove that a camera could work on Venus, that the surface was visible in ambient light, that the terrain was geologically diverse and scientifically interesting, and that the environment was actively hostile in ways that required extraordinary engineering to survive even briefly. The next chapter of that visual record requires solving problems that the Soviet engineers could not solve with the materials and knowledge available to them in the 1970s and 80s. Those problems have not been solved yet, but the scientific case for solving them has only grown stronger as the remaining questions about Venus have become clearer. The surface of Venus is the most hostile environment a spacecraft has ever been asked to operate in for an extended period. It is also, in terms of fundamental planetary science, one of the most important environments in the solar system to understand. That combination of difficulty and importance is what makes the Venera archive so significant, and what makes the absence of any new data from the Venusian surface since 1982 so notable. The orange rocky plains visible in those restored panoramas are not just historical curiosities. They are the best direct view science has of a world that holds some of the most important unanswered questions about how planets work. There is a deeper philosophical point embedded in the story of the Venera program that is worth examining. The images from Venus were not easy to take. They were not the product of pointing a sophisticated camera at a beautiful landscape and pressing a button. They were the result of 15 years of systematic failure, analysis, redesign, and retry by a generation of engineers who kept returning to a problem that kept defeating them, getting closer each time, extracting a little more data from each failure than from the last. The knowledge that the surface of Venus was even partially visible came not from a theoretical prediction, but from a decision made on incomplete information. The Venera 9 engineers attached a floodlight to their lander because the models said the surface would be dark. They also programmed the camera to scan immediately upon landing in case the floodlight worked and illuminated something worth seeing. When the lens cap came off and the sensor immediately detected natural ambient light, that was a discovery that no model had predicted with confidence. The image that followed, the sharp angular rocks under the diffuse orange sky, was a surprise on multiple levels simultaneously. This is how planetary exploration actually works at its best. Not as a process of confirming expectations, but as a process of confronting reality with the best instruments that can be built and accepting what those instruments report back. The models had been wrong about the pressure, wrong about the darkness, wrong about the wind, wrong about the rock shapes. The instruments that survived long enough to make measurements corrected those models one data point at a time. The Venusian anomaly, the way the planet has confounded expectations at almost every step of its exploration history, is not evidence that Venus is mysterious in any mystical sense. It is evidence that predicting the behavior of complex planetary systems from first principles and limited data is genuinely difficult. The atmosphere of Venus follows the same physical laws as the atmosphere of Earth. The rocks on its surface were formed by the same geological processes that operate elsewhere. The anomaly is in the specific combination of conditions that Venus presents, not in the underlying physics. Understanding that combination in full detail is the work of future missions. The tools available to planetary scientists in the 21st century are substantially more capable than those available to the Venera engineers. Computational fluid dynamics can model the Venusian atmosphere in far greater detail. Materials science can produce thermal management solutions that were not available in the 1970s. Electronic systems can be miniaturized to a degree that reduces the internal heat generated by the probe's own functioning. Communication technology has advanced to the point where data transmission rates that would have seemed impossible to the Venera engineers are now routine. What has not changed is the fundamental physical environment. 475 degrees Celsius and 90 atmospheres is still what awaits any machine that reaches the surface. The laws of thermodynamics have not been revised in favor of Venus mission designers. The heat will still penetrate any container eventually. The pressure will still find any structural weakness. The challenge is to extend the operational window from 1 or 2 hours to something longer, long enough to conduct more comprehensive science, perhaps to emplace instruments that could continue to operate, or at least passively survive, and transmit data after active electronics have failed. Some proposals have considered high-temperature batteries and passive sensor systems that could continue recording environmental data, temperature, pressure, and seismic signals, long after the active electronics in the lander had succumbed to the heat. A pressure vessel that remains structurally intact even after the electronics inside have failed would still contain a record of the last values measured before failure. Recovering that data might require the use of a relay satellite in orbit, which could ping the surface package periodically and receive whatever residual signal the system could produce. This kind of mission architecture, where different components of a system are designed with different operational lifetimes and different scientific objectives, is becoming more common in planetary exploration as scientists try to maximize the scientific return from the enormous cost of any deep space mission. A Venus lander that was designed from the outset to operate in 2 phases, an active phase of 1 to 2 hours for photography, drilling, and detailed measurements, followed by a passive phase of days or weeks for environmental monitoring, would extract far more information from a single mission than any previous Venus surface probe. The decision-making framework for which missions to pursue involves not just scientific merit, but also the maturity of the technology required. A mission concept that depends on engineering solutions that do not yet exist carries higher development risk and higher cost than one that uses proven technology. This is why current proposals for Venus surface missions tend to be technically conservative, building on what is known from the Venera program and from subsequent materials in electronics research, rather than betting on breakthroughs that may or may not arrive on the schedule that mission development requires. The scientific community's interest in Venus has increased notably in recent years, driven partly by the expanding field of exoplanet research. Thousands of planets have now been discovered orbiting other stars, and the question of which planets might be habitable is one of the central questions in contemporary astronomy. Venus-like planets, rocky worlds at or slightly inside the inner edge of their star's habitable zone, are common among the discovered exoplanet population. Understanding what makes Venus inhospitable, when it might have been hospitable in the past, and what processes drove the transition, has direct implications for assessing the habitability of those distant worlds. If Venus had liquid water oceans for a significant fraction of its early history, then the habitable zone around a Sun-like star extends further inward than current models suggest. If Venus became uninhabitable relatively quickly due to a combination of its proximity to the Sun and the early Sun's ultraviolet output, then the habitable zone is narrower. The outcome of this scientific question affects estimates of how common life might be in the galaxy. This is perhaps the most unexpected connection in the story of the Venera program. A series of Soviet engineering missions designed to beat American spacecraft to the surface of a neighboring planet, missions whose legacy is a set of orange panoramic images of rocky plains taken by scanning mirrors behind tiny quartz windows inside cooling titanium spheres, has become directly relevant to the search for life in the universe. The connection runs through the planet's history, the question of what Venus was before it became what it is now, and through the planet's atmosphere, the question of what chemical signatures might indicate biology in environments where conventional biology is impossible. It runs through the engineering problem of building machines capable of surviving environments that would destroy conventional spacecraft. Because the same problem arises when designing telescopes and instruments to study exoplanetary atmospheres from a distance. The Venera engineers solved one version of this problem imperfectly, but well enough to produce the only direct visual record of the Venusian surface that exists. Whoever solves the next version of this problem will expand that record for the first time since 1982. The scientific questions waiting on the other side of that engineering challenge are among the most significant in planetary science. The orange rocky terrain is still there. The atmosphere is still filtering sunlight down to its warmest wavelengths. The surface is still being renewed by volcanic processes whose timing and scale remain uncertain. The clouds are still concealing whatever chemistry operates at altitude, whatever might or might not explain the ultraviolet absorption that has puzzled researchers for nearly a century. None of these questions have been answered by orbital observation alone. The planet closest to Earth is also, in terms of direct surface observation, among the least known places in the solar system. That situation is the result of the extraordinary difficulty of working in Venus's environment, and it is also the result of the decisions made by space agencies over the past 4 decades about where to direct limited resources and attention. Mars received the attention that Venus did not, and Mars is now one of the most comprehensively explored worlds accessible to spacecraft. Whether Venus receives similar attention in the coming decades depends on scientific priorities, engineering progress, and commitments that have not yet been fully made. What is certain is that the images from the Venera program, now restored with modern digital processing to reveal details that were invisible in the original transmissions, are not just historical documents. They are active scientific data being studied and reanalyzed by researchers working on questions about planetary geology, atmospheric physics, and astrobiology that could not have been fully articulated when the images were first taken. The 4-decade-old data from those titanium spheres continues to inform science being done today. That is the lasting significance of those extraordinary missions. Not just that they answered the questions that motivated them, but that they created a record capable of answering questions that had not yet been asked. The scientists who designed the Venera landers could not have known that their panoramic images of Venusian rock would eventually be analyzed in the context of searching for life on exoplanets. They built instruments designed to survive long enough to look at the surface of a neighboring planet and report back what they saw. They succeeded, partially and briefly, against conditions that were actively trying to destroy their machines. The record they created stands alone, and it stands incomplete, waiting for the next eye to open in that orange-lit world. The Soviet planetary program that produced the Venera missions operated under conditions that are difficult to fully appreciate from a modern perspective. The engineers working on these probes were dealing not only with the technical challenges of building spacecraft capable of surviving the Venusian environment, but also with the organizational and political constraints of working within a state-directed scientific program during the Cold War. Access to materials, computing resources, and foreign scientific literature was limited in ways that modern research teams do not face. International scientific collaboration on mission design, which is routine today, was largely unavailable. Despite these constraints, the Venera program achieved a sequence of firsts that have not been repeated. The first probe to transmit data from the surface of another planet was Soviet. The first photographs from the surface of another planet were Soviet. The first color photographs from the surface of another planet were Soviet. The first audio recording from the surface of another planet was Soviet. The first soil sample analysis from the surface of Venus was Soviet. This sequence of achievements represents the output of a scientific and engineering tradition that was operating at the absolute frontier of what was technically possible at the time. The lessons encoded in the design evolution of the Venera landers, from the crushed aluminum sphere of Venera 4 to the color imaging, audio recording, drilling titanium complex of Venera 13, represent a compressed course in applied planetary engineering. Each mission was a proof of concept for the next. The transition from passive pressure resistance to active thermal management, from black and white imaging to color composite photography, from simple temperature recording to multi-instrument surface science, happened in about 12 years and under conditions of genuine uncertainty about whether any of it would work at each step. The engineering principles developed through the Venera program remain relevant to contemporary mission planning even though the specific technology has been superseded. The principle of designing for a known operational window rather than indefinite survival, the use of phase change materials for thermal management, the preference for mechanically simple and thermally robust imaging over electronically complex systems, the practice of over-engineering structural components relative to predicted loads to account for model uncertainty, these are approaches that any future Venus surface mission would rediscover independently if the Venera heritage were not available to inform the design. The telemetry from the Venera missions also included atmospheric data collected during the long descents through the Venusian atmosphere before each lander reached the surface. These descent measurements, tracking temperature, pressure, and chemical composition at different altitudes, provided a detailed vertical profile of the Venusian atmosphere from the cloud tops to the surface. Combining measurements from multiple descent probes at different latitudes and longitudes built up a picture of how the atmosphere varies across the planet and with altitude. This atmospheric profile data confirmed that the lower atmosphere of Venus below the clouds is relatively stable in temperature and composition compared to the cloud layers above. The temperature drops steadily with altitude, from around 475 degrees at the surface to below zero at the cloud tops. The pressure drops exponentially with altitude. Below the cloud layers, the atmosphere is clear and relatively transparent, which is why the Venera landers found adequate natural light at the surface despite the thick clouds above. The cloud layers themselves, extending from roughly 45 to 70 kilometers altitude, are optically thick in visible light but have regions of relative transparency in certain infrared wavelengths. These infrared windows in the clouds allow some thermal radiation from the surface to escape upward, and they have been exploited by orbital instruments to make indirect measurements of surface temperature variations. This is how the possible evidence for recent volcanic activity detected by the Venus Express spacecraft was obtained. By sensing the slightly elevated infrared emission from regions of the surface that might have experienced recent lava flows. The Venus Express mission, operated by the European Space Agency from 2006 to 2014, was the most recent spacecraft to study Venus from orbit before the planned future missions. It made extensive measurements of the atmospheric chemistry, the cloud dynamics, and the surface thermal emission. It detected hydroxyl radicals in the upper atmosphere, confirmed the presence of lightning, tracked the day-to-day variations in the atmospheric superrotation, and found evidence suggesting that the Venusian volcanoes might still be active. When the mission ended, the spacecraft was deliberately lowered into the atmosphere for a final aerobraking experiment before contact was lost. The Parker Solar Probe, primarily a mission to study the Sun, has made several gravity-assist flybys of Venus on its way to progressively closer solar approaches. During these flybys, it has detected faint surface emission in near-infrared wavelengths through the atmospheric windows, adding new data points to the incomplete picture of Venusian surface temperatures. These observations are brief snapshots rather than sustained surveillance, but they demonstrate that orbital observation with appropriate instruments can extract some surface information even through the thick cloud cover. The Bepi-Colombo mission, a joint project of the European Space Agency and the Japan Aerospace Exploration Agency, is on its way to Mercury, but has also made Venus flybys, collecting atmospheric and magnetic field data. Venus continues to be observed as a target of opportunity by missions passing through the inner solar system, even as no mission currently in operation is dedicated exclusively to studying it. The scientific case for a dedicated Venus mission has been articulated repeatedly in planetary science priority surveys. The United States National Academies of Sciences, Engineering, and Medicine produce a planetary science decadal survey every 10 years that sets priorities for the next decade of planetary exploration. Venus has featured prominently in multiple decadal surveys as a high-priority target for both orbital and surface investigation. The challenge has been translating scientific priority into funded, developed, and launched missions in an environment where multiple high-priority targets compete for limited budget. The cost of a Venus surface mission, particularly one ambitious enough to extend operational time significantly beyond the Venera baseline, is estimated to be high. The development of new high-temperature electronics, advanced thermal management systems, and pressure-resistant instrument packages requires substantial investment. The mission architecture needed to deliver a capable lander to the surface, while also maintaining communication through a relay orbiter, adds complexity and cost. These factors have made Venus surface missions difficult to advance through agency planning processes, even when the scientific motivation is widely recognized. Private spaceflight ventures have begun to express interest in Venus, motivated partly by the possibility of more cost-effective mission architectures enabled by commercial launch vehicles and partly by genuine scientific interest in the planet. Whether private missions will be technically capable of delivering surface science instruments to Venus in the near future remains to be seen. The engineering challenge does not become easier because of the funding source. But increased interest from multiple directions does create more opportunities for the technology development that ultimately makes missions possible. The broader context of planetary exploration in the coming decades includes substantial activity across the solar system. Missions to the outer planets, to the asteroid belt, to the Moon, and to Mars are in various stages of planning and development. Venus must compete for attention and resources within this crowded landscape. Its scientific importance is not in question. Its accessibility, in engineering terms, remains challenging in ways that other destinations are not. The history of exploration suggests that difficult destinations eventually receive the attention they deserve when the questions they can answer become sufficiently compelling to motivate the investment in solving the access problem. For Mars, that process took decades but produced a sustained campaign that has transformed scientific understanding of the planet. For Venus, the foundation was laid by the Venera program and has not been built upon in the surface exploration dimension for over 40 years. The foundation is still there. The images are still there, restored and studied by researchers who were not born when they were taken. The scientific questions they generated, and the new questions identified by subsequent research, are still there waiting for the instruments that can address them. The orange rocky plains under the amber sky are still there, unchanged on geological timescales, waiting for the next pair of eyes that will open on them and report back what they see. When that happens, the data will be compared to the Venera panoramas, rock shape by rock shape, horizon by horizon, to determine whether the specific sites captured in the 1970s and 80s are representative of the broader Venusian terrain, or whether they were unusual in some way. The comparison will tell scientists something about geological variation across the planet's surface. The new data will address questions that could not be formed without the baseline that the Venera program established. The scientists who built and operated those titanium spheres, who extracted 23 minutes of temperature data from what appeared to be a dead transmission, who discovered that the surface was not dark, that the rocks were young and sharp, that the world was not sandy but basaltic, that everything was orange, who recorded the first sounds from another planet and missed their compressibility measurement by a lens cap's width. Those scientists and engineers created the foundation for everything that comes next in the exploration of the planet closest to Earth. What comes next depends on decisions not yet made, technology not yet developed, and missions not yet launched. The gap between the last Venera image in 1982 and whatever comes after is already more than 4 decades long. The science waiting at the other end of that gap is real, important, and not available by any other means. The Venera program's legacy extends into the way scientists think about what it means to study a planetary surface. The idea that you can build a machine, send it to an environment that will destroy it, and extract meaningful science during the brief window between arrival and destruction is not an obvious one. It requires a kind of planning under terminal conditions, accepting from the outset that the instrument will not survive indefinitely, and designing its operational sequence to front-load the most important measurements into the earliest moments of its life on the surface. This approach is different from how long-duration missions are designed. A Mars rover is built to operate for years, with systems designed to be repaired, updated remotely, and adapted to conditions encountered during the mission. A Venera lander was built for a one-way trip with a fixed operational window. Every decision about what instruments to carry, what sequence to run them in, and what data to prioritize for transmission was made with the knowledge that the mission would end after roughly 1 hour and that no second chance would be available. The sequencing decisions made by the Venera engineers were not always optimal. The Venera 14 compressibility measurement failure is the most vivid example. A piece of protective hardware landed in the wrong place and ruined one of the primary surface science objectives. There was no way to move the hardware, no way to redirect the arm, no way to retry. The machine was programmed with a fixed sequence, and the environment provided an unexpected input that the sequence could not accommodate. Future mission designs have to grapple with the same constraints, but with more sophisticated tools for dealing with unexpected inputs. Modern landers can carry onboard computers capable of recognizing anomalies in real time and adjusting their operating sequence accordingly. A contemporary equivalent of the Venera 14 scenario, a lens cap landing on the measurement target, might be detected by an onboard camera system before the compressibility arm deployed, and the arm might be redirected to a different spot. These capabilities exist now, and would be incorporated into any new Venus surface mission. But the fundamental constraint of the operational window remains. Whatever thermal management system is used, the window will eventually close. The surface of Venus will eventually overcome any insulation, any phase change material, any cooling system that a lander can carry. The question is not whether the window will close, but how wide it can be made and what can be accomplished within it. The measurements that scientists most want from the Venusian surface in the 21st century go beyond what the Venera program could achieve. They include high-resolution mineralogical analysis of the surface rocks and soils, which requires spectrometers sensitive to wavelengths that can identify specific mineral compositions. They include seismological measurements to understand the internal structure of the planet, which require sensors capable of detecting and recording ground motion over extended periods, potentially spanning multiple seismic events. They include detailed meteorological measurements of the near-surface atmosphere, including wind speed, turbulence, and the flux of heat between the surface and the lower atmosphere. They also include photography, but photography at a resolution and field of view substantially beyond what the Venera telephotometers could achieve. Modern imaging sensors are orders of magnitude more sensitive and higher resolution than the scanning systems of the 1970s. A contemporary camera system, capable of surviving Venusian conditions, even for a limited period, would produce images of the surface with detail that would transform the scientific understanding of the terrain. All of these measurements, combined into a single mission, represent an ambitious scientific program. Achieving all of them within a 1 to 2 hour operational window requires extraordinary prioritization. Extending the operational window requires solving engineering problems that are currently unsolved. The two goals are linked. The better the thermal management, the more science can be done, and the more science motivates the engineering investment. This is ultimately the situation that Venus science faces. It is a scientifically important destination with unique characteristics that make it extraordinarily difficult to reach in the sense of operating instruments there effectively. The difficulty is real, but not insurmountable. The Soviet engineers proved that machines could work on Venus. They proved it repeatedly across a decade of missions, with progressively more capable systems. The question for the next generation is what it will take to go back and do more. The orange-lit rocky surface is the beginning of the answer, not the end of it. The Venera images tell scientists what to expect when they arrive. They provide a ground truth that radar maps and orbital spectrometers cannot provide. They show the texture and scale of the terrain, the clarity of the air, the quality of the ambient light, the way rocks lie against each other, and the way the horizon looks from the surface. This is the kind of information that shapes mission designs before they are finalized. The difference between designing instruments for a landscape you can see and designing them for a landscape you can only infer. More than 40 years of inference have followed those original images. The next set of images will be the first ground-level update to a visual record that has been frozen since 1982. Whatever they show, they will be compared to what the Venera cameras saw and interpreted through the lens of everything learned in the intervening decades. The science that comes from that comparison will be worth the engineering effort required to make it possible. That is the case for returning to the surface of Venus, stated in the simplest terms. The existing images are extraordinary documents of scientific and engineering achievement. They are also the starting point of a visual record that has not been continued. Continuing it requires solving hard problems. Solving hard problems is what planetary exploration does when the scientific motivation is sufficient. The surface of Venus is waiting. It has been waiting for more than 4 decades. The questions it can answer have not gone away. They have only become more precisely understood, more connected to broader scientific questions, and more clearly in need of new data that only instruments on the surface can provide. The story does not end with the last transmission from Venera 14 in March of 1982. It pauses there, mid-chapter, with a set of instruments that exceeded every expectation the scientists of the 1960s had for what was possible on that world, and fell short of every ambition the scientists of the 21st century have for what understanding that world will require. The pause has lasted more than 40 years. It will end when the engineering is ready, and the scientific commitment is made to send the next machine into that orange sky and down through 90 atmospheres to the rocky surface below, where the light is soft and diffuse, and everything is some shade of amber, and where the air itself will begin immediately working to reclaim the machine from the humans who sent it there.